Hi everyone, in this video we are going to talk about calculating the order of reaction, right, using clock reactions and also tabulating data into a table and solving them. So this is one of the very common questions that you will face when you are answering kinetics questions where you have clock reactions where they give you the time, right? So if you take a look at this reaction, sometimes they'll tell you the volume of A mixed with a volume of B, or a concentration of A mixed with a certain concentration of B, right? And they tell you the time taken for certain phenomenon to be observed, and you can use 1 over t to approximate rate. So let's take a look at a greater detail of what this actually means. Okay, so the first thing that I want you to pay attention to is this idea of rate is equal to a change in concentration over the change in time. So since we start from 0, then we will uh, just take concentration over time. But the main idea is the change in concentration over the change in time itself. Okay, so what is important for us to take note is that as long as this concentration remains constant, right? It doesn't change from experiment to experiment. Rate is proportional, inversely proportional, right, to time, if and only if the concentration used for each experiment is the same. So what do I mean by this experiment and what do I mean by the same? So the first thing that we need to do is to identify the kind of experiments that we are doing. So it is very important to know what experiments we are doing before we can get down to the theory questions. And so the clock reaction there are two kinds of reactions that we usually look at. We look at the sulfur clock and also the iodine clock experiment. Alright, so in the sulfur clock we have this X over here, and what we want to see is that after we pour the reagents together, you will start to see cloudy suspensions forming, and by the time you see this X being obscured, this means that it has reached a certain concentration, all right, which is a proxy. All right, so we are using our sense of sight to as a proxy for concentration. So the moment it covers the cross, we are certain that a certain concentration, which is fixed in our opinion, has been formed, and we can use that time to calculate that rate. So in this case, it's fairly straightforward because the concentration, which is how much solid must be formed to obscure the sulfur clock, to obscure the cross, has to be formed, is always the same. Right. In the second example, which is the iodine clock, this is the one that a lot of students do not understand. So basically, we have this reaction. H2O2 reacts with I minus to give you I2, which will react with starch to give you blue-black coloration. However, this blue-black coloration is quite immediate, and it is quite difficult to see how much it obscures the sulfur clock itself. So what we want to do is to add in a fixed amount S2O32 minus, alright, and what happens is that since this is fixed and is limiting, right, every single moment I2 is produced, it will immediately react with S2O32 minus to regenerate our I minus. Alright, but the important thing is that immediately after it's formed, it is removed by the S2O32 minus until a certain concentration of S2O32 minus has been used up. So that's why if we fix this, we are technically fixing the concentration of S2O32 minus. Okay, so if it takes 5 seconds for the blue-black coloration to appear, it means it takes 5 seconds for all the S2O32 minus that I've added into the solution to be completely used up, such that the next I2 that's formed will react with starch to form the blue-black uh, complex. Okay, so this is very important. Why is this important? Because in extreme cases, alright, in some MCQ questions, they like to change the concentration of S232 minus, and so this concentration at the top is no longer constant. Therefore, if I multiply this S2O3 concentration by 2, technically my rate, uh, technically the amount of time required to get rid of this S2O32 minus should also multiply by 2. So this is what we want to take note of. Okay, so with that, let's take a look at this table. Right, so we know that rate is inversely proportional to 1 over t if concentration of whatever we are looking at is constant. Okay, either the amount of sulfur that needs to be produced to obscure the X, or the amount of S2O3 that was added that needs to be reacted away before blue-black coloration can appear. Okay, needs to be constant before you can use this. So if we record the time, alright, we have to take the reciprocal of that, which gives us x, 2x, and 2x over here. Okay, and we can use our concentration of A and B, and we can use the very simple method of looking at how the concentration of A has multiplied by 2, but B stays the same, and the rate goes up by 2 times, so it is first order with respect to A. Whereas in the second case, this stays the same, but this divides by 2. Nothing happens to the rate itself, so it's zero order with respect to B. So you would expect B to appear in one of the fast step, and one of A to appear in the slow step itself. Alright, so this is how we can tackle graphical questions using such a method. And so this is the qualitative method that we have just done, but if we want to use the quantitative method, we can actually use our trusty rate equation. So we can have rate is equal to K times A to the power of A, B to the power of B. Alright, so assuming I'm comparing these two experiments, I got the value of rate is equal to x over 2x. Okay, x over 2x is equal to k. A is 1 to the power of A. This is 2 to the power of A. I'm using these two values here. Then I have 2 to the power of B, 2 to the power of B, which are these two values over here, if you can see. So what I will get is x and x cancels, k and k cancels, these two, they are the same. I get 1 over 2 is equal to 1 over 2 to the power of A, therefore A is equal to 1. So this is the quantitative method of solving things. But of course, if the qualitative method is a lot more efficient, stick with that. Okay, and the quantitative method will allow you to solve even the tougher questions. So if all else fails, just use simultaneous equation. So I hope this helps you to understand how we can determine order of reactions of clock reactions. Okay, so this is very important. Please take some time to re-watch this video for a couple of times to really understand how the various experiments actually work and how the data is tabulated and how you can eventually go about calculating the answers.